All right, welcome everybody to the last day of week 9. We have got some technical talkings at you going on for today. We're going to be talking about the stack versus the heap versus just letting C++ do it, you know? So, one of the reasons why people think C++ is a hard language to learn is because you're kind of forced to know all this stuff about RAM and memory and loading and storing and, you know, what's kind of going on inside of your CPU and RAM and stuff like that. That used to be true. So you used to kind of have to have a pretty good understanding of what's going on with the memory map to write C++ code. Nowadays, you can probably get by for a while at least, just letting C++ handle it for you. And so there's a much gentler on-ramp onto C++. It's not as abstracted from the real world, the hardware, as like JavaScript or Java is. It's still closer to the hardware than that, but a lot of what we talk about today is important if you were living in the 80s and 90s and is still kind of important today. You kind of have to know it, but a lot of times there's just a better way, and it's sort of secondary importance now. Okay. So this is the last day before you drop, so I'm going to hit you guys with probably the hardest lecture as far as, computer architecture and stuff like that today, so you can find out if, you got what it takes to stay in the class for the remaining 9 weeks. So here we go. Let's do this. Okay. So this is what RAM looks like. Like top-down view of your computer. You got a CPU, you got some sticks of RAM in there. Modern day RAM oftentimes has RGB glowing on it and stuff like that. But if you were to like zoom in like really close on the RAM, somewhere within the RAM is going to be your program. Okay? And your program is laid out like this in memory. So your program always starts at memory address 0 and goes up to 7FFFFFFFF. It's a hex number. You don't need to know hex yet. Just know that if you ever print out a pointer or something and you get a hex thing that's 7FFF, that means it's on the stack somewhere. So there's a couple different important segments that you have to kind of know about. Let me zoom in here. So the very bottom of the memory is called the minefield of doom. This is a highly technical term that I invented. So if you ever try accessing the minefield of doom, what happens when you step on a minefield? Anyone know? I used to live in an area that was kind of an active minefield. In San Diego, Camp Elliott, artillery field, World War II, tons of unexploded ordnance throughout the areas and the canyons of my homes back then, and yeah, you die. And in fact, in 4th grade, some kids found a artillery shell on the sidewalk and picked it up and played catch with it, and it blew up and killed them. So my high school didn't like the fact that our AP Bio instructor was constantly taking us into the canyons, walking around. We were looking at nature and stuff like that. It was I learned a lot, but they were always afraid that we would step on a mine and die, or unexploded ordnance and die. So yeah, so what's happening here is this is creating a integer pointer, right? And the integer pointer is pointing at memory address 0. So this is not an integer holding 0. This means pointer is pointing at memory address 0. Okay? And by the way, there's a quiz on the type on the quiz, which I'll go over in a second. But this here is saying print what is at memory address 0. So it's trying to do a load. It's trying to load from memory address 0. And so what happens is you touch the minefield and you die. Okay? So segmentation fault, core dumped. The operating system detected that you tried accessing memory near 0. And it's not just 0 if you try reading from memory address, 100 or 1000. it'll still core dump. Like, the minefield of doom is pretty big. You know, it's a highly technical term that you will not see in any other class than here. But that's, I think, a pretty good description for it. So if you touch the minefield, you die. Okay. Above the minefield is the code segment. The code segment is marked read-only, RO, usually. There is such a thing as self-modifying code, which is kind of cool. We don't really do it very much anymore due to security reasons, viruses and things like that. But there's kind of a cool way of programming where, like, you run your program and then you modify your program while it's running. So, for example, if you have a bunch of if statements that you don't need, like you read through the data files and you're like, oh, you know, none of these values are negative, then you can go through your program and pull out all of the checks for negative data and make your code run faster. You know, we basically don't write that anymore. Okay. So, yeah, basically this is just a curiosity, just in case you're wondering where your program is. All the assembly instructions, they're here in the code segment. Then above the code segment is the BS segment. So the BS segment, the BSS, as we call it, holds globals. And there's actually a couple different chunks of the BSS. But if you ever make a variable that is in global space, and high equals 10, this is held in the BSS. Which is different from the stack, which is what normal variables are allocated on. This is a regular, boring stack allocated variable. Let's make it not 10, let's make it 20, just so it's a little bit different. Okay, so you can see the memory address of high is substantially far below the address of bi. Bi is up in the stack. The stack is the very top of memory up here. The BSS is down here. Okay. The actual numbers don't matter. That's just some location in RAM that's where the value lives. Okay, it's a street address. Okay. So, still cannot find the technical term for it. Yeah, I don't know, dude. It's just that's just what I call it. I call it the minefield. So then accessing using globals is generally considered bad practice. The stack, which is where your normal variables live, like by, you know, int, if you make int x, double y, char z, they all live up here in the stack. And there's a few reasons why we don't use globals very much. First of all, it just makes better logic usually to pass a variable to a function and then have that function return something. It makes more sense for it to go on the stack. That said, if you have a variable that gets passed to every function everywhere, like if you have a map, like a world map or something, literally every function you have takes that map as a parameter. A global's fine, especially if it's read-only. Read-only globals are kind of fine. That's not a big deal. But if you're just passing a variable to every function, it can get kind of verbose, and there's probably a performance penalty on that as well. So sticking variables that are used by every function into a global, yeah, I've seen people do that. It's okay. Mildly, but there's a bigger problem when you get into multi-threading. So if your program has multiple threads running within it, so for example, if you're writing a video game and a thread is like a program within your program, so you can have one program running, subprogram, a thread running for like each of your AI in the game, and if they're all reading and writing to the same globals, then they can overwrite each other's values. Like one could read a value, and one could read a value, and then one could add 10 to it and write it, and then this guy adds 10 to the original value and writes it, and now rather than that value going up by 20, it went up by 10, and so each thread has its own stack though, so each thread would have its own variables, they don't conflict. Globals can cause problems once you get into multi-threading, so in general, good practice involves minimizing the use of globals. That said, you know, you're not gonna see me really complaining too much about them if you make them smart. Okay. So above the BSS is the heap segment. The heap segment is where we're going to be talking about today. The heap grows upwards, and then we have something called the stack that grows downwards. And the stack is where your normal variables live. So let's explain how the stack works, first of all. So, what happens between the CPU and the RAM is that the CPU is going to issue like a load command to the RAM. So like when you want to mess with the variable, it'll be like, hey, give me the value at memory address, whatever. And then it sends a load command over there, and then the RAM sends back, okay, the value there is 437. You're like, all right, cool. You mess with it a little bit, and then you maybe add to it or something, and then you store back into that memory address again, and then the variable gets updated. So there's kind of this transaction system between RAM and CPU. The CPU loads values from RAM, does things with them, and then writes values to RAM. And that's kind of what's going on under the hood. Your regular variables are stored in stack. Okay, so let's zoom in on the stack and see what's going on here. So stack's at the very top of memory. Top of memory is 07ff ... And so all of the variables in main are up at the top. So if you have an integer x, and actually, what do we have over here? We had high and by or something. We had is it high and by? They live here. Now let's say we call a function. So we call a function called max or something. And we're going to pass in two variables to max. Like let's pass in high and by, and it's going to figure out which one of those two is the greatest and return the result. So what happens is that the parameters get pushed onto these stacks. So you have something called the stack pointer here. This whole thing is called the stack. And the stack pointer is just a memory address. Like maybe the memory address right now is at 7,000 or something. And when you pass parameters to max, a lot of times they go onto the stack. And they look something like this, and high and by, we pass those two things on, and maybe we're going to return a value. So you might have like return value on here as well. And when you call the function, what happens is this stack pointer moves down. And so the stack, the bottom of the stack is now, that was kind of cool. Bottom of the stack is now here. And you have like an old stack pointer, it's called the frame pointer. The old stack pointer is like up here. And then this function is going to run, it's going to do its thing, and maybe it calls another function. Well, if it calls another function, let's say it calls swap or something. Let's go back to the rainbow font. Let's say max calls swap, and swap's got 10 variables in it. Int x, int y. I don't know why I'd have 10 variables. Let's just say int w. What happens is that all those variables are also on the stack, and so the stack pointer moves down again, like this, to wherever the bottom of those variables are. And so you can see, looking at RAM, high is still there, the original high back in main is still there, the by in main is still there, the copy of it, because this was like, let's say it's called by value, the copy of it is in max, the copy of it's in max, max has its own variable called return value, and then it calls swap, and then swap has its variables. All these guys are still in RAM, they're still there. So when you come back up, when swap returns, what happens is this stack pointer comes back up to the old stack pointer. All these guys get deallocated. And then like maybe there's a return value that's passed up to max. Then when max returns, the stack pointer moves up again. These values get deallocated. And the upshot is you do not need to worry about allocating or deallocating memory. It's nice. So what would that look like? Let's say we've got... put you back, I guess. Let's got a function. Yeah, high wouldn't be on the max. Or actually, high is not actually on the stack here, is it? It's down in the BSS, right? So high is like way down here somewhere. High, it's like down here somewhere. Okay. It's way down south in the land of cotton or something. Okay. So the pointer moves down when you call a function. Yeah, every time you call a function, the stack pointer moves down. Every time you return from a function, the stack pointer moves back up. So, and when it moves down, what that's doing is allocating memory for all of your little local variables and things like that. So when you call max, the stack pointer moves down. It actually can pre-compute in advance how far it needs to move down. It moves down far enough that there's room for all the different variables here. And then when it returns, the stack pointer moves back up, and all those variables are automatically deleted from existence. So high is actually like way down south over here somewhere. Okay. Does that make sense? So whenever you have a variable, just a regular variable, it's on the stack. We call them stack allocated variables, even though that's not technically in the C++ standard. The standard actually doesn't refer to the stack and the heap at all. There's sort of a difference between like the standard and like the standard way things are implemented, and they're not technically the same, but the stack and the heap are what programmers talk about, and so that's the terms that I use. Technically, these things aren't in the C++ standard, but it's how it's done. Okay, so yeah, so the stack pointer moves down every time we call a function, moves up every time you return from a function, and so the stack kind of does this over the time. Okay, now let's talk about the heap. So the heap is way down south. It's above the BSS. Heap's down here, let's say. Heap. Why is it called the heap? Historical reasons. The stack makes sense. Like the stack, it's like a stack of papers. Every time you call a function, you put another paper on top, right? And every time you return from a function, you take a paper off, and the paper has all your variables on it. Does that make sense? So you call a function, that calls a function, that calls a function, that calls a function. If you do that too much, you get a stack overflow, right? So if you have a function void Bob, and Bob just calls Bob, right? Then that's an infinite loop, and it's like false. Why? Because every time you call a function, the stack pointer moves down. And on our system, the stack has the max stack size on our system is 100 megabytes. Okay. So every time Bob calls Bob, and Bob calls Bob, and Bob calls Bob, and Bob calls Bob, what happens is that this thing starts going, right? And at some point, it's going to cross this imaginary dotted line. Swap here. There's a dotted line, and that is the segment boundary, right? That is the maximum you can do. Okay. And if the stack pointer ever crosses that, then the operating system goes, nope, you're dead, and it kills your program. Okay. So as long as you're calling functions and returning from functions and calling functions, returning from functions, you're fine. If you ever call a function that calls a function that calls a function that calls a function that calls a function, and it crosses this imaginary dotted line, it's not really imaginary anymore, is it? It kills your program. And that's to keep your program from infinite looping recursively. Right? What would the stack size be on your PC? Is it your CPU? No, it's set by the operating system. So if you're actually curious, you can type limit. Limit. Yeah. So right now it's theoretically 8 megabytes. In theory, the stack size is 8 megabytes. But in practice, I've noticed it doesn't kill your program until you go over about 100. So this is kind of a soft limit, I think. It's set by the operating system, though. The heap is unlimited. Memory use is unlimited. You can have 1,000 files open at once. 15,000 processes running at once. max nice of 0. Now if we become Portnoy, it looks like your limits are the same, I guess. Okay. Is there any way a normal program could go over the stack limit? Yeah. Yeah. It happens occasionally when you have a really small stack. Like if you have a K for stack, which I've done before, like if I'm doing multi-threading, like you want to have a bunch of different programs in your program running, give each of them like a K of memory. You can actually run through that just through normal usage. Like a function calls a function, which calls a function. You can run out of stack space. It can happen. Then you have to bump up the stack space. In my Quake server, it would run out of stack space occasionally just through normal usage. Nothing really obscene. But it had a really small stack also, so I bumped that up. From an 8 megabyte stack, you're probably going to be fine as long as you stick to primitive variables, but you can run out of stack space even with just one function call. Watch. You know, the amount this thing moves down is based on the size of the variables here, right? Do you guys know any variables that are bigger than 8 megabytes that you've learned, like in the last, I don't know, lecture or two? Anyone? Any variables that can hold, oh, I don't know, 1 million integers? Let's say 4 megabytes. Oh yeah, like a multi-dimensional array. Yeah. Speaking of which, yeah, let me well, okay. Let me just show you how quickly you can crash a program. Bob is now non-recursive. Integer array. Allocate 40 megabytes. Okay, so theoretically this should crash our program. Let's see if, because I'm exceeding the soft limit, let's see if it actually crashes though. Yeah, okay. Now if I turn this down to 1 million, which is 4 megabytes, works fine. Okay, so that is instant karma, right? Instant death if you make a large array on the stack. Okay, we're going to use the heap for that instead. If you need a large array, use the heap instead of the stack. Okay. So let's talk about the quiz real fast because there was a typo on it, and so I'm going to give all of you a free point on the quiz because of that. So week 9, day 2 quiz over here. But yeah, a multi-dimensional array could crash it as well. The first question was not an error, and only 13 students out of the, what is it, 59 left in the class at this point. We started with around 70 something, so we've lost about 15 students or so. Not too bad. Although, I don't know, after today, you guys might be, ah. So the question was last time, remember, you've got a 2-dimensional array, and you're mapping those 2D coordinates to 1D coordinates, right? So every time you go down a row, it's like traveling right a number of columns equal to the width of the array, right? Like, we talked about this last time. Every time you go down, that's like traveling right 5 times, right? Because the width of it is 5. Every time you go up, it's like you subtract 5. Every time you go east, it's like adding 1. Every time you go left, it's like adding 1, subtracting 1. Yeah. So the algebra is this: row times the number of columns plus columns. But I don't expect you to memorize that formula. You know, it's a mapping from a 2D coordinate system where you've got a row and a column. You're mapping to a 1D index and an array. Here's the algebra. You take the row times the width of the 2D array, which is the number of columns, and add columns to it. But I don't expect you to memorize that equation, because you should just be able to look at it. At least that's how my brain works. Like, I need to be able to look at things and be like, okay, if I go down twice, then that's like going right 10 times, right? And so for the homework assignment, for the quiz rather, going down twice when there's 13 columns, that's like 26 to the right. And then 5 more to the right past 26 is 31. Okay, so the next quiz assignment will have another one of these row major ordering questions on it. And there will be a question on stack versus heap as well, which is our topic for today. So the second question had an error that should have been an ampersand x instead of an x. This actually won't compile. You cannot put an integer into a pointer. So two different types. A memory address, even though it's actually technically an int, it doesn't compute. C++ by default will prevent you from just taking an integer and sticking it into a pointer. The only number it allows that for is 0, which is kind of a bit of a weird trivia point. So what this was supposed to say was at x and at y. And so pointer would be pointing at y. It then dereferences the pointer. When you remember the unary star, the dereference operator, and the missing reference operator are polar opposites. Like plus and minus, multiply and divide, they oppose each other. And so if you set pointer equal to reference y, when you do star pointer, that's as if I had written the word y there. Okay, because pointer holds the memory address of y, like y is at memory address 1000. And then when you do this star pointer, it says give me the variable at memory address 1000. Well, that's y, so it's like as if I'd written y there. Then it increments y by 1, so it prints out 9002. But all of you guys are going to get a free point for that, so my bad, mea culpa. All right, so yeah, so instant crash. If you by the way, there's a new Zybooks up. The Zybooks is going to cover some information we haven't talked about in class yet, because the Zybooks people teach the topics in a different order than I do. So if you get too far ahead, you're going to run into classes, and we haven't talked about classes yet. So just like chill on it, you know, like don't be like, you know, I don't, what? Did Kearney talk about this? No, I haven't talked about it yet. We'll talk about it next week. So you might want to, you know, some of the because we're doing pointers right now, right? So I wanted to give you the Zybooks for pointers, but some of it does mention the topic from next week. So just, you can skip those parts until we talk about them. Okay. But if you want to look at the pointer stuff, yeah, it's up there now. Due next Wednesday or something like that. Okay. So let's go back to this. Nope, that's the wrong one. Let's go back to this. Okay. So the heap. Let's talk about the heap. So the heap lives over here. And again, the actual ordering of this stuff doesn't matter particularly. It's just so you can sort of visualize it in your head. The heap grows upwards. The stack grows downwards in memory. And there is a heap boundary and a stack boundary, and if those segments ever cross the boundaries, you get a stack overflow, segmentation violation, seg fault. That's another way of putting it. Have you guys ever played tennis? Do you know what a fault is in tennis? Or a fault in bowling? So if you're serving in tennis and you step over the line, that's a fault. Okay, sport you play is Wii Sports. I don't think you can fault in Wii Sports. Right? I don't think you can. You always serve perfectly. The bowling, it's a lot more rare to step over the line in bowling, you know, because you're kind of, that's the whole point of bowling, is to get up to the line and do it. But I guess you could slide over, possibly. So when you step over the line, that's called faulting. And so that's why in this server, when you make a little bit too big a thing, Let's compile it. Segmentation fault. Fault means you stepped over the line. Segment refers to these different segments of memory. The stack segment, the heap segment, the BS segment, the code segment, and the minefield of doom, which, you know, is just my own term. You're not going to find that online. It's not something the Jedi would teach you. Okay. Have you faulted in Wii Sports? That's cool. All right. Yeah, I don't remember there being faulting in the game, but maybe in the bowling? I don't know. So, 100-pin bowling is pretty fun, though, in that game. Just that pad. That's funny. Okay, so let's talk about the heap. So the heap grows upwards. And the heap is accessed by using two new keywords that we're learning today. And the two new keywords are called new and delete. So, so we'll stack allocate 40 megabytes. It's called instant crash time. So rather than doing that, we are going to heap allocate. Which is cool. Works just fine. So the syntax is going to look like this instead. New is the new keyword for today. Learning points for today. Understand the memory map as a sort of conceptual thing. And then new keyword allocates memory. And then we'll get to the delete keyword. Deallocates. And it allocates memory until deleted. Okay. So normally when you have a variable, when you hit the close curly brace, those variables go away, right? Like if you have a for loop, int, or a while true loop, just make it easier to type. If you make a variable inside of here, this variable goes away when we hit the close curly brace, right? Vim got confused by the close curly brace. It's funny. Didn't auto-indent right. Okay, so this is going to allocate 4 bytes of RAM for the integer, and then it goes away here. Technically, it's probably going to be allocated when the function gets called and deallocated, but whatever. Do you guys understand that? Like a normal variable lives within its scope. A normal variable lives within the curly braces. Do you guys understand that? Like a regular variable, int x gets allocated here, then x goes away, deleted, deallocated, however you want to call it. Here. Okay. Not true for new. So this memory does not get deallocated when you hit the close curly brace. So we call this function Bob, and Bob is going to leak 40 megabytes of memory. It allocates 40 megabytes, and then it doesn't deallocate them. They're gone. If we look at the memory usage of our program, it just popped up by 40 megs, and we can't access it anymore because this variable doesn't exist anymore. That variable's gone. We have no way of getting out of that 40 megs of memory. We just lost it. Misplaced, leaked 40 megs of memory. And this is a very common bug in a lot of programs. They knew things and they forget to delete them. And so the memory usage of like Firefox for years, they had an open ticket for over a decade that Mozilla Firefox was leaking RAM. So you left your browser open, the memory usage would creep up over time and never go down. And the only solution was to quit Firefox and relaunch, and the memory usage would reset back to normal because they were doing news without deletes. The only way of recovering the memory is by quitting the program, because the operating system knows where you are on RAM. They know where you live, and they come over with a bulldozer and they just kind of take out your house and pave it over and put flowers on it and stuff. Actually, they don't. They actually leave everything as it was, but they sort of deallocate it. They just say, okay, that's free memory now, and it could change over time or something. But the OS knows where you live. The OS knows where your boundaries are, and just comes in and wipes it all out at the end. So you can't hurt the server by doing this, right? If we call this code here and run it, we didn't hurt the server. We didn't just permanently allocate 40 megabytes of RAM because it quit. The operating system was like, oh, you don't need that anymore, and it cleans it up for you. So there's actually so if you need more space than is provided, you need to take care of allocating and deallocating memory yourselves. Yep. Unless you use a vector, which is what I would do. But for your homework assignment, it uses pointers. So if you don't declare Bob in main, does it still take up 40 megs? Nope. Because if Bob isn't called, it never does the new. And even worse, check this out. It's a lot of leaking. Better get some depends. Right? So if I come in here and let's make this even bigger. Let's make this a 4 gigabytes of RAM. And we're going to put the inline in there because inline always flushes, right? Especially when your code's going to crash. If the code crashes without you doing a flush, a lot of times the whatever you see outed vanishes, right? So if you don't have an inline, a new line will flush as well. For cout, new lines, by the way, trivia point, a \n does not flush on a file write, only on cout. So there's a small trivia difference there. So let's leak 4 gigs of RAM and see how that works. Works fine. Let's do it again. Works fine. The system only has 4 gigs of RAM, by the way. Ooh, it might be optimizing this way. Ooh. Yeah, let's not do that. I have the optimizer turned on by default, so let's turn off the optimizer. Nope, still works. Okay, cool. The optimizer, by the way, can figure out that this isn't being used by anything and delete it. That's actually the kind of stuff that that optimizers do. Because, you know, let's say I put in here int array 1 billion integers. This should crash, right? You guys concur? That should crash. I mean, we crashed with 4 megabytes, right? We're now putting 4 gigabytes on the stack. This is stack allocation. We do not have 4 gigabytes of stack. You all concur? Excellent. That's from Catch Me If You Can, Leonardo DiCaprio and Tom Hanks. Great movie. Great movie. Was it crashing earlier? Yeah, remember this? Remember this? Instant crash time, right? Just a little stack allocation between friends. Compile, run, works fine. What? What? I just stack allocated 4 gigabytes. What? Do you know why? I just told you about 2 minutes ago. Because I'm not using it. Yeah. Let's use it. Array 420 is equal to 9001. Works fine. I don't know what you're talking about. Works fine. Remember, the extra credit is due today. If you went to the BIM talk, you have to write an essay. Works fine. I don't know what you're talking about. It's A-okay. All right, check this out. If I turn off the optimizer, crash. The optimizer is very, very smart. The optimizer is, in fact, smarter than most people. And it knows what's up. And in this case, what's up is that all this code is going to do, this is a really, really tedious and time-consuming way of outputting the number 9001 to the screen. So the optimizer does this. That's what the optimizer does. It pulled out allocating 4 gigs of RAM, accessing something in an array. No, because it knows every time this code runs, it's going to output 9001. So it just deletes all of your code and puts 9001 in there. So if you turn the optimizer off, your code crashes. And if you have the optimizer on, it works fine. So, kind of cool, right? A little bit terrifying. It's terrifying because sometimes you turn the optimizer off, your code breaks. You're like, what? I thought the optimizer... What? I thought it was supposed to just make my code run faster. Nope, your code can actually break when you turn the optimizer off. So, any downsides to the optimizer? Yeah, that's one. It hid the fact that we had bad code, right? A lot of times, if you have bad code, the optimizer knows you have bad code and deletes it. Like Google got a massive hack attack because they had a sanity check in their code. And the optimizer could prove to itself that sanity check would never happen. And it removed it. And and that sanity check was in there to keep them from getting hacked. And so it was a very subtle bug. Because you don't see it. You don't you just see your source code. Like, it doesn't tell you it's doing this. Right? It doesn't do the, it doesn't edit your source code. It's behind the scenes. It's just making things faster. And it pulled out a very essential security check that ended up getting them hacked as a result of it. So it does slow down compile time a little bit. Not too noticeably though in most cases. Like a 25%. Something like that. How do you find small bugs in big programs? Great question. There's a whole field around testing software and learning how to write tests and how to do continuous integration. So every time you make an update to your source code, it runs the test suite on it, verifies that you haven't broken anything, and there's it's a whole lecture on that. It's a big field though. It's a big field. Code verification. Okay, so let's talk about the new kind of thing. So what new does? Let's return it so it's not quite so terrible. Actually, let's actually see if we can get this to crash. Okay, so let's do this in a while true loop. So we're just going to keep leaking 4 gigs of RAM over and over again. Let's turn off the optimizer because I think the optimizer can prove that those arrays aren't doing anything. So the optimizer probably just pulling out, So let's turn off the optimizer, run it, and there we go. So it actually allocated, I'm scrolling up right now by the way, it actually allocated a lot of RAM before it died. Okay. So you'll learn how that works because the system only has 4 gigs of RAM total in the entire system. So how did it allocate so much RAM? Let's I'm actually kind of curious. Int x equals 0, cout plus let's see how many times it runs. So it actually ran, wow, quite impressive. Oh. I turned the optimizer back on. Let's try this again. There we go. Yeah, the optimizer's like, you're not using that. Deletes it. Okay. So 35,000 times it leaked 4 gigs. So our hard limit on the heap size, we can actually compute from this. So 35,183 times 4 gigs is 140 terabytes of RAM. So when I allocated 140 terabytes of RAM, then it's like it had enough, and hard closed me down. Okay, so not bad, no, for a system with 4 gigs of RAM. Could I use all of that? No, but it would certainly allocate it for me, no problem. All right, so that was a little bit fun. Let's go to find out how big Heap can get. Do you understand what I did there, Tim? I just kept allocating 4 gigs over and over again. I only have 4 gigs of RAM, that's right. But the heap grew to be like over terabytes in size, right? 125 terabytes in size. I can't use all of it, but remember I wasn't using it. It just allocated it. So the system was like, sure, buddy, you got 125 terabytes. I'm like, all right, now give me 126. Oh, no, that's too much. Segfault. So that's the hard limit. If you type limit, you can see that the data size, which is another name for the heap segment, the data segment, it's unlimited. It's not quite unlimited. Apparently 125 terabytes is our limit on that. It's it's not just 4G, it's 5G. It is. It's allocating. I can't use all of it. If I actually tried writing to all of that, it wouldn't work. But just allocating it, and you'll learn why that works in CSI 45. CSI 45 goes into how the whole memory subsystem works and things like that. But for your purposes, just be like, the heap can be really big. Okay, the stack's 8 megs. The heap is large. Okay. CSI 40 is just magic, yeah, basically. Okay, so that was fun. That was a fun little exercise. So let's talk about deallocating things. So let's have Bob return a pointer here. Return R. Okay, so you guys see what I'm doing now. I'm allocating 4 gigs of RAM, and I am going to return a pointer to it. So the pointer is to the first element in that giant array that I created. And then let's bring Bob back to life, like Evanescence. And we'll say int pointer R is Bob. And then we will teach you the new command. Deallocate the memory allocated in Bob. Okay. Are pointers the same as arrays? Yes. Pointers are arrays and arrays are pointers. If you have a variable here called x, I can make a pointer to it. Okay, that closed curly brace is killing me. I can make a pointer to it like this. And see out x index 0. Let's give that a value. And this will output, sorry, not pointer. Okay. Yeah. This will output 420. Okay. It's a pointer to an integer. So if I say give me the first integer at that memory address, that will be x. And yeah, pointers and integers are pointers and arrays are interchangeable. There's one very small caveat on that, which is that arrays have their size information hidden within them in the scope in which they're created. So you can actually find out how big an array is, a stack allocated array is when you make it. But that's kind of pointless because you know anyway. for all intents and purposes, a pointer is an array and an array is a pointer. They're interchangeable. Okay, so here is our second big thing here. The delete keyword deallocates memory, and if you delete an array, delete keyword. So the delete keyword deletes memory for a regular variable, and then the delete square bracket operator, which looks like this, deallocates an array. And there's historical reasons why those are different. Kind of bad historical reasons, but reasons nonetheless. Okay. So do you guys see what's happening here? So Bob is going to go onto the heap. Here's the heap. And we say new. Give me 4 gig bytes of memory. And so the heap has something called the break pointer. And this moves up by 4 gigabytes. And so this is, well, that's R, I don't call it. Yeah. And then we're up here at the, so we're in the stack, you know, we're in a function called Bob. Bob's kind of got its thing going on. Let's make that font size a little. It's got int pointer R, and it's got X, and what else does it have? Another pointer in there. It's got int X, it's got int star pointer. So when you call Bob, the stack pointer moves down. It allocates 2 pointers and an integer. This value is pointing at R down here in the heap. Okay. And this pointer is pointing at this guy here. When Bob returns, it returns this return value here. And these two guys go away. These guys get obliterated from existence. R gets returned back into main. So main now has int star R, and that's pointing at the value down here. Okay, so even after Bob returns, all these things go away. Stack pointer, oops. Stack pointer moves back up to here. Because we return that value, it can still point at the array down there. Okay. So main now has a pointer to this big 4 gigabyte array down in the heap. Now if we were to call new again, the break pointer would move up some more, and we could have more and more and more arrays on here. But these things, do you see how this thing did not move even when we return from the stack? So when we return from the stack, this didn't change. The heap is permanent storage. The heap sticks around. It doesn't go away when you return from the stack. That's the big thing. Okay? Regular variables go away when you return. When you have a heap allocated object, it sticks around until you call delete. And when you call delete, then yeah, sure. It comes in here, array's erased, and the break pointer moves back down here maybe, and then if you tried using R, because R is still around, right? We could still access it, but we're going to be touching unallocated memory at that point. So if we delete R and then say R, 5 is equal to 420, this is bad. Compiles just fine. Segfault. Why? Because and it didn't have to segfault, by the way. It's undefined behavior. But because the breakpoint moved down here, I tried accessing memory above the edge of the heap. So this whole memory is now out of bounds. I segfaulted. Fault. Stepped over a line. Foot fault. Yeah. So after you delete something, don't mess with it anymore. What if you double delete? What if you try deleting this thing twice or 3 times? What do you guys think is going to happen? You delete something multiple times. Remember the rule of the Sith. Every new has 1 delete. Every master has 1 apprentice. For every new you have, you must have 1 delete exactly and only. What do you think is going to happen with a double or a triple delete? Anyone want to put some money down on this? Segfault. Yep. Yep. So it doesn't have to. It's undefined behavior, I think, at that point, but it's going to be a segfault, right? But this is proper behavior. Okay. So now we've got 1 new, right? We've got 1 new up here. This new matches this delete. 1 new, 1 delete. Good to go. If we don't do anything, then you're going to be. That's also a crash. If you delete something that wasn't newed, that's a crash. If you knew something and delete it twice, that's a crash. If you knew something and you don't delete it, that's a memory leak. Not a crash, though. That's why Mozilla Firefox leaked memory, because at least it doesn't crash. A lot of companies just prefer leaking memory and then just, telling people to reboot once a day. That was Microsoft's thing. My friend worked for a defense contractor, and they noticed that Microsoft Windows was leaking memory for a mission-critical defense system. And so Microsoft said, every day at midnight, reboot your systems. And Windows back then actually had a bug in it where their clock would overflow once every 180 days or so. And nobody ever knew that. The bug was in Windows for like over a decade or something. And nobody ever found it because no Windows machine had actually made it 180 days without crashing. So the official advice from Microsoft was turn it off and turn it back on again once a day. And just hope you don't get attacked when you're rebooting. So, attack at midnight, right. I once went down to the San Diego jail to bail out a friend of mine. He flipped off a drummer at a concert. The drummer jumped off the stage and got into a fight with him. And my friend got arrested for it. Not the drummer. He's like, you suck! And flips him off. And the drummer's like, what the hell did you say? He's like, you suck! And the drummer leaps off the stage, comes over, and the police come and arrest my friend. So I had to go get him at the San Diego jail at 3 o'clock in the morning. And I was there till 4 o'clock in the morning because the San Diego jail turns its computers off and on again at 3 a.m. I'm like, I would like to pick up my friend, please. They're like, you can't. I'm like, why not? The computers are down. And every day at 3 a.m., you just can't get anybody out of jail. And I was just sitting there just like... So this is correct, though. So we got 1 new, we got 1 delete. This is good. So if we run this code... the optimizer's turned back on. Let's turn the optimizer off. And you'll see that it is... Oh, it's not leaking anymore. I should change that message. No problem. You see that? It'll just run forever because it's newing, it's deleting, it's newing, it's deleting, it's newing, it's deleting. It's actually not leaking RAM. Yep. Works just fine. So, what are the trade-offs here? I think you guys can see one important trade-off. So the trade-off is what? When to use stack variables and when to use heap variables. Use heap when you need a what? What's the obvious use here? Very large array. Yeah, when you need a big one. We need a large array. Use stack for primitives like ents, There's absolutely no reason to like new an int. Yeah. Int pointer, new int. No, don't do that. Yeah, big storage. Okay. Also, use heap when you want something to be permanent until deleted. Use stack when you want a variable to automatically die at the end of scope. Right? So if I make a variable here, x, it automatically dies here. Right? I don't need to waste my brain power thinking about I don't have to move the stack pointer down, I don't have to move the stack pointer up, it's all automatic. And in fact, the auto keyword used to look like this. So you used to actually mark a variable as auto, and that meant it's a stack variable. And so you can see that it still is technically in the standard, even though it's not really. So you can say a variable is an auto variable, which means it's a stack allocated variable. And you're like, but wait, I thought that was stack allocated. Yes, that's why nobody used it that way. But because that was an official part of the standard, they had this keyword called auto. Nobody could have made a variable named auto. Like if you try making an int named auto, well, that auto is fine, but if you make an int called auto, it doesn't work. It's a reserved keyword. Okay. So they had this keyword, and so they repurposed it. So they made auto x, right? All right, we've already got an x, y, right? So that's where the auto keyword came from. It's because they had that keyword, they weren't using it for anything. Okay, is using heap slower? Yep, heap is slower. Heap is slower, stack is faster. The amount of speed, yeah. If you're allocating a million things a second, you probably shouldn't be. Typically, you're going to new something. Like if you're newing 4 gigs of RAM, you're probably not going to be doing that 1,000 times a second. You know what I mean? Or if you are, your code's wrong. Normally it's like you launch a program, you allocate an array, you load from disk into it. That's the normal use of new, in which case the speed difference is negligible, right? If you do one new at the beginning of program launch, you are not even going to be able to measure, even in microseconds, the difference in time. Okay. Okay. Yeah. So let's do this. See what I did? R is now a stack allocated variable. Okay. And I'm returning R. Why is this bad? Why is this really, really, really amazingly bad? I'm returning a pointer. I'm returning a pointer to something that's on the stack. And then I'm returning from the function. There's no heap anywhere in this code now. Everything is now stack allocated. I just switched R from being heap allocated to stack allocated. I'm returning the memory address of this spot in stack. Then I'm deallocating it automatically because I'm returning from the function. Every time you return from the function, all the local variables get deallocated. Yes, this memory has been deallocated. And I'm returning a pointer to the start of the memory that's been deallocated. And so if I use it, R10 equals 420. Segfault. Why? Because I now have Bob, rather than newing R, it's like a pirate, right? R. It's now on the stack. And so what happens is that we're returning, rather than int pointer R in main pointing at the heap, it's now pointing at this memory location. Then the stack pointer goes back up. This memory is deallocated, but we have a pointer at deallocated memory. We try accessing it, and then it's past the stack boundary to segfault. This is really, really bad coding. Okay. I mean, while it existed, we had R square bracket 0, we had R square bracket 1. All these guys were up in here. And then when we return, they're all deallocated. They're outside of the boundaries now. Would it work if you called the array outside of the function like a global? How does allocating multiple blocks in memory work? Can it get crammed? Yeah. So if you new things and you delete them, it turns into a jigsaw puzzle, right? And the stack's very easy. The stack can't get jammed. Every time you call a function, stack moves down, right? It's pretty simple. Every time you call something, stack moves down, stack moves down, stack moves down, you return, stack moves up, call a function, stack moves down, stack moves down. Can't get stuck. Can't get stuck. Now, just have that red spot stuck to it. Oh, the heap, though, turns into a jigsaw puzzle. So you might have this block allocated for array A, and this block allocated for array B, and this block allocated for array C, and then you call delete on array C, and you've got some open area in there. And then you allocate D, and D is about half the size of C, so it'll probably split that and put that in there. And then you try to put C back, but there's no room for it now, so now C has to come up here. And so the break pointer has to move up. And so break pointer, no, lost the B, there we go. No, lost the L too, okay, or the, there. So the break pointer moves up here, and then we deallocate it again, and the thing can fragment. So the new system, new, which is based on something called malloc, or that's the old way for it, it's actually complex. It's actually a very complicated thing to write. Because you have to recognize when, like if I have C here and then I delete A and D, I have to recognize that all that area is now a big contiguous block of memory, that if I wanted to allocate something that was like that big, it could fit in there. And so it's a jigsaw puzzle. When you start off, it's really easy. You just allocate, allocate, allocate. Once you start deleting and reallocating, then your memory can get fragmented. And the thing has to try to keep fragmentation from happening as much as possible. It has to consolidate adjacent open areas into one contiguous open area. This is writing malloc is typically done as like a memory allocator. Is typically done as like a junior level semester long project, or maybe not semester long, but it's like a thing. Like it is no joke to write it. It is no joke. It's like, yeah, it's like junior level computer science to come up with one of these things. The stack's easy. Let's move the stack down, move the stack up. Handling that without fragmentation is yeah. So it's a beast. It's a beast of a program. So you don't have to do that in this class. Now, let's talk about your homework assignment. So for your homework assignment, you're going to have, let's just delete all this. Okay. So int main. So for your homework assignment, you're going to have a function that right now looks something like this. Getting carpal tunnel. Might have to stop early today. I'm going camping anyway, so won't be the worst thing in the world. It would suck to have to put up a tent. Where are you camping? I'm going out to Bakersfield. beautiful Bakersfield, Oildale area, camping among the oil pumps. Nah, I'm kidding. All right. I do historical reenactment type stuff. Put on armor, hit people with sticks. It's fun. Doing sea shanties tomorrow night. It'll be fun. So file name and do this. So for your homework assignment, this is the way that it's structured right now. And this is why we're going over all this stuff, because a lot of people write with pointers. Pointers were very common in the 80s and 90s. Modern C++ doesn't use it as much, which is why you guys haven't seen it until now. But you still need to know it, especially if you're going to work with like the Linux kernel, which requires pointers, or if you're working with people that like coding in the 80s and 90s style, which this homework assignment is. And so you need to become at least familiar with what's going on. Okay, so let's take a look at this. Let's say that you're making a game. The game is going to load data from disk. You're making Hydro Thunder. You're going to load all the data for the Grand Canyon map. And this function here is going to be passed a file name, grandcanyon.txt, whatever. It doesn't have to end in text, by the way. A lot of students think that every time you open a file, it has to end in text. Nope, you can pass in whatever you want. And then we're going to pass in size by pointer. So this is just like call by reference, except we're passing a pointer instead. Behind the scenes is exactly the same as call by reference. The syntax is going to look a little bit different in the C side of things. So let's do this. So let's start off by saying string s is equal to read. Please give me a file name or something. Or not. I'm not your... Okay, please give me a file name. And then we are going to say int pointer r is equal to load map s and size, which I need to make also. Enter size equals 0. So I'm going to pass in size by reference. Notice this is basically the same thing as call by reference, except the syntax is a little bit different. So the ampersand is here rather than here, because what's happening is I've got a variable called size, and I'm passing the address of size in to this here, which takes a pointer. So it's a pointer to size. And this is, for all intents and purposes, the same thing as call by reference, except size up here is a pointer. And so if I want to set size to be like 420 or something, I have to do this. Dereference the pointer, and that gives me this size out here. So this variable is being set to 420 using this syntax. Bernie Strustrip thought this was a little bit excessive, and he changed it to look like this instead. It's the exact same code. It's the exact same code, just less stars. Because stars are scary. People are scared of pointers. And so this code here is the same as this code here. It'll compile exactly the same way under the hood if you look at these simply. It's the exact same thing. When you do call by reference, you're passing a pointer in. It just doesn't look like it. There's one difference, which is that pointers could be null, but we haven't talked about that yet. So as far as you know, it's exactly the same. There is actually a small difference, though. Do you have one of those carpal tunnel bracelets? I actually don't get carpal tunnel. That's why I'm a little worried by this, because I code a lot, and I don't get carpal tunnel ever. So I'm going to probably just call it early today. That was actually annoyingly painful. Okay, so I'm hoping that standing up will make a difference too. Okay, so now we need to open up the file for reading. And we're gonna have, okay, so ifstream ends, opening up file name, and then we're gonna do a loop while true, and then we're gonna do this the old-fashioned C way, or the C++ way, and pointer r is equal to new int. How many integers are we going to read from the file? Do we know? Do we know how many integers are in this file that the user hasn't given us yet? Do we know in advance how big we should make this? Yeah, we don't know. And this is actually one of the big issues that I have with the old way of programming, which is like, I don't know what number to put here. I don't know how many elements are in that file until I've read through it. You know what I mean? Like, I guess I could read through the file. And count, and then close it, and then open it again, and then allocate an array of that size. Sure, let's do that. It's horrible. Let's do it. Let's do it the proper way. Okay. So, let's see here. Int temp equals read from the file x plus plus if we hit the end of the file, break. So this is going to be called ints in file. Okay, so then we're going to close the file, and then we're going to reopen it. Super annoying. Super annoying. That's why I use vectors. In the previous class, I just allocated an array of size like 1,000 or whatever, and then just hope that it doesn't have more than 1,000 in it. It's a terrible system, because you make those numbers way too big just in case, you need it, but then you end up wasting RAM. Whereas with the vector, you just start with the size 0, and you grow it to whatever size it needs to be. So. Okay, so let's do this. We now know how many ints are in the file here. Okay. So int pointer r equals new int. Ints in file. So we're actually going to allocate the right number here. And now we can do a for loop instead of a while loop. For int I equals 0, I is less than ints in file, I plus plus. So we know there's 50 ints in there. Okay, cool. So we allocated enough room to hold 50. So we just say array square bracket I equals read from the file. So it's going to open the file and read it a second time, and this time pull all the data out into the array. So the first time through the array element 0 is going to be the first number in the file. Next time through the loop, I is 1. Array element 1 is the second number in the file, and it's going to keep doing that over and over again. I'm using my read library here to make the code simple and easy to read, because it's better than IF streams by default. Okay. And then at the end of the day, we are going to return R. So main is going to be given a, oh, actually that's just called size, isn't it? Huh, yeah, okay. So star size is equal to ints in file. Actually didn't need ints in file, I could use size, oh, either way. So I'm gonna set size, that's how many ints we read. So I'm gonna pass that out as a call by reference parameter, essentially. It's called the call by pointer. That's basically call by reference. And then, yeah, so if we read 50 variables in from the file, size will be set to 50. Then down here in main, we can do another for loop. Move that to the top of the screen. For int I equals 0, I is less than size I plus plus. Out r square bracket I, and there we go. So this is, it's yelling at me for something. Yeah, that's fair. For int I equals 0. Don't talk and type at the same time. It's always, my brain can't handle it. Okay. Give me file name, Crente. So if we look at what's in Crente, Crente has 10, 20, 30, 40, 50, negative 10, 0, 163. Our program is, in fact, loading the values from Crente and putting them to the screen. There's only one thing we forgot to do, and what was that? What did we forget? The thing that people at Firefox forgot. People at Mozilla. They forgot to do the same thing. This is why new and delete sucks, because you have to keep track. Delete, very good. I forgot to delete R. And that's the killer thing. This is like I said, it's like an unsolvable problem. And so what happens is that when you get a pointer like this, there's no information in the type if I own it or not. I don't know if I'm, by owning it means I'm responsible for deleting it when it goes away. There's nothing in the type that suggests to me whether I own it or whether I'm just like pointing at something. Because like there could be like a big array and you could pass me a pointer to part of it and I could read through part of it. And that's a non-owning pointer. But if you're returning if you're allocating memory here and you need to tell me like, here's the keys to the car. You have to turn it off when you're done with it. You know, you're like, there's nothing in the language itself that indicates if this is an owning pointer or a non-owning pointer. In other words, it doesn't tell me, am I responsible for deleting it or not? And that's a problem. So there have been various proposals to fix things like that. There's an owning pointer type that basically indicates, yes, you own it. And if if it goes out of scope without being deleted, then you can make that either a compiler error, or you can make it a you can call the destructor on it and automatically clean up the memory. This is why the old ways are bad ways. Let me show you how I would do the homework. I would do the homework not playing by the rules. So it looks like you're supposed to learn about call by pointer, returning pointers that are arrays, dynamic memory. It looks like that's the point of the assignment. But maybe the point of the assignment is to teach you why vectors are better. And maybe what you can do to solve the assignment is convert from an integer pointer to returning just a vector. So you could return instead a vector of integers from a different load map function. Doesn't need size because vectors include their size information with them. So this is this is how code was coded back in the 80s and 90s. And it's still valid. Like I'm not even dogging it. It's just like this is the way that things were done back then, because there wasn't anything better. And then this is C++ 11 and beyond style. Okay, so there's two competing. Like C++ is a Frankenstein of a language. Like there's a lot of old stuff in it that just like people don't use anymore. There's old stuff like this that people do use quite commonly. This is actually not an uncommon way of coding, because people are used to it, and it works if you know what you're doing. And then there's the modern way as well. And so Frankenstein they just sew on a new arm, to the chest, and they glue a second head on top of the head. And C++ has grown like a Frankenstein monster over the years. But the good news is if you just stick to the modern stuff, like it actually results in fairly nice and clean code that doesn't cause these kinds of headaches we're talking about. So let's do an alternative to this using modern C++. So I'll start off by copying and pasting this code here. So we're going to open the file for reading, and I'm just going to do this while ends. So I'm going to be returning a vector, right? Okay, so I need to make a vector of integers named vec. And I'm going to return vec. So I'm going to make a vector and then return it. And that vector is going to contain all the map data. Then for my reading process, I'm going to read to a temporary from the file. Temp stands for temporary, not temperature. So I'm going to read into a temporary variable. And then if I went off the edge of the file, I am done. Otherwise, I'm going to add it to vec. Okay, real simple. Noticeably less code. All right. This code here versus this code here. It's quite a difference in size. 21 to 16 lines of code versus 9 lines of code, so it's almost half the size. Also, this code here is reading through the file twice. So it's actually going to take twice as long to run, because it reads through the file to count how many elements are in it, closes it, and then does it again. And are there better ways? Sure. Arguably. You can implement something kind of like a vector, I guess. Or you just say maximum size is 1,000 and just pray that you don't go over. Or, I don't know. There's kind of no good options with the top thing. So if you run this on the server without deleting the array, would it remain in memory? Yeah. What would happen? Oh, no. Like down here. Like if you did this. Did I just eat up 40 megabytes of the server permanently? No. When your program quits, the operating system knows where the beginning of your RAM was, the end of your RAM, and it comes in with a bulldozer and just wipes out all the segments. Everything's gone. Nothing survives the operating system's purge. You cannot kill Linux by forgetting to free memory. That's one of the reasons why operating systems exist, because they don't trust programmers to write bug-free code. So the operating system is a layer that sits beneath all of that, and it handles the memory allocations and the deallocations. And when you quit, it's like, oh, you screwed up, like you didn't deallocate everything you needed to, and so it just comes in and it deallocates it all for you at the end of the program. So that's why I said a lot of people just leak memory, because they know the OS will clean up after them. And you got. Oh, sorry, we got a leak. Yep, that was fun. That was a leak in real life. Aquarium leak. Okay. Not a memory leak. Water leak. So, is Bridges due on Wednesday or Friday? Whatever it says on Canvas. Is it on Canvas? It should be due Wednesday, I think. So, yeah. So if you forget to deallocate memory, that's the least bad thing you can do. But even still, it's bad because your memory usage will creep up over time. Okay, so always follow the rule of the Sith. 1 new, 1 delete. Okay? And that can be tricky to follow. If your code calls this function in multiple places, and it's passing those pointers around, keeping track of when it's done, when it should be deleted, it's a tough one. Use a vector instead. So let me show you what happens with the vector instead. Okay? So is this vector heap allocated or stack allocated? It's not a pointer. It's not nude. All right? So it looks like it's stack allocated, but can a vector hold more than 100 megs? Yes, it can. So it's both. There's a stack allocated component and there's a heap allocated component. The little person here named vec is on the stack. And when it goes out of scope, and when you add things to it, it's got another section of itself that's on the heap. Okay? And so when you push back, that's actually growing on the heap. But this part here is actually just a couple of pointers behind the scenes. And it just keeps track of where the beginning of it is and where the end of it is. And when it goes out of scope, like if I didn't return anything, and it just went out of scope, vec would be deleted here automatically. Because this is a stack variable, right? Stack variables automatically go away when you hit the closed scope, right? So it deletes it. And vec has on itself something called a destructor. A destructor is a function that runs automatically when it gets destroyed. And so when you destroy vec here, then it calls its destructor, and it goes to its spot on the heap where it has its memory and purges it. So it handles it for you. And this is why I like vectors a lot. Like if I wasn't married to my wife, I would marry vectors, because that's how nice they are. Okay? You no longer have to track who is responsible for deleting memory. Newing memory is easy. This is the easy part. This is the hard part. If your code looks like this, with all these different branches and ifs and elses and the other things, trying to figure out if every single possible branch through your program ends up with a delete and only one delete, that is a very, very difficult problem. With vectors, they figure it out for you. When they go away, they purge the heap. They purge their chunk of the heap. Simple. Super, super simple. Now, let's talk about this. What the hell is this doing? What are they doing over there, cat? You know. What is this doing? So we've got two. We don't actually have echo here. Okay, so let's make a new one over here called vector of ints, and I'm going to call this person Stover. Okay, so Stover is going to be equal to load map, passing in the file name, and then we're going to say for every integer in Stover, we are going to see out that integer. Okay, so also simpler, right? Because you need all of this code. You have to, for a normal C-style array, you have to keep track of the size, and you have to keep track of the pointer separately, and hope they line up. And you can't use a range explorer with them because it doesn't know how big it is. With a vector, you can just do this. 2 lines of code instead of 6. Okay. Vectors are just nice. They're really nice. So, what is going on here? What is this line of code doing? We got vec. We got Stover. What is happening at this interface between the two bits of code? Load map is making a vector. Behind the scenes, all a vector is a pointer to a dynamic array. It's literally that. It's just a new int array. That's all it is behind the scenes. Nothing actually that fancy. Vector just has a pointer to the beginning of the array and a pointer to the end of the array, so it knows how big it is. That's about it. Nothing really fancy. So what happens here? What's this line doing when we're returning it? Because we got a vector here, and it's pointing to some big chunk of memory. It might have a gig of map data loaded up. We don't know. And we return it. What is happening here? Is that going to go and copy all billion elements from vec into Stover? That seems inefficient. Right? This is pretty straightforward. An int pointer is just an integer, right? And so load map is literally just returning an integer. That's easy. Boop, there you go. It returns an integer, and technically it's kind of returning the size too. So it's returning the starting memory address and the size, which is, for all intents and purposes, the same thing that's in a vector, right? The vector has 2 pointers, beginning and ending. Same thing. So what's going on here? What's happening? Are we going to have to do a copy of a billion elements? If so, we don't want to use vectors, right? Like if we had to do a billion copies out every time we loaded a map like this would be really slow. It'd be, very inefficient. If the pointers are being passed, the heap portion is being destroyed at the end of the function, right? Yeah, vec is getting destroyed here. But as of right here, it's not dead yet. And so, C++ says if you're passing out something that's about to be destroyed, you don't have to. You can pull a tricky. You can pull a tricky. Okay. So what happens is Stover, which has a pair of pointers to the beginning and the end of the array, currently pointing at nothing because it doesn't have any elements yet. What it does is it reaches into the guts of vec, and it sets its beginning pointer to vec's beginning pointer. And it sets its end pointer to vec's ending pointer. And it just kind of takes ownership of that array. And then vec goes away, doesn't deallocate it because it's passed its ownership to somebody else. Vec pops like an empty balloon. It's like you got 2 balloons, you squeeze all the air out of one into another or something. I don't know. The analogy doesn't work too well. But basically, when you hit return vec and vec's about to go away, it steals the guts of vec and puts it inside of Stover. And that's just 2 integer copies. It just copies 2 pointers. That's it. And then vec sets itself into a state saying, I've had my guts ripped out. Don't delete me. Or there's nothing to delete. So when it goes around, so when it goes away here, so when it goes here, there's nothing left inside of vec. It's had its guts stolen. It's in Stover. Didn't have to copy a billion elements. It just goes pop, and it goes away. Doesn't cost anything. Stover has now a billion elements in it from that function without having to copy them all out. The only expense was, what you'd expect, which is reading from the disk. You have to read from the disk a billion times, grow the vector, which takes a little time. And then when you pass it out, there's a very tricky little maneuver that happens all behind the scenes. It's all automatic. That's what's really nice about it. You don't have to implement this. The code does it automatically. It reaches in, pointer, done. Mine. This is mine now. It moves ownership from the old one to the new one. Is it copying the values or the memory addresses? Just copying the pointers. So vec over here has, like I said, a vector behind the scenes is just 2 pointers. That's all it is. 2 pointers to a spot on the heap. So somewhere on the heap, it's been growing all the map data, and so the vector has pointers to it. And when you return it, because you're returning an object that's about to be destroyed, that enables a certain optimization where instead of having to copy all billion elements, which is slow, it just copies the pointers. Beginning pointer, ending pointer, and done. That's it. No more. 2 operations. And then when vec goes away, vec probably has a note in itself saying, I don't have any data in me right now. I'm empty. And so when the deleter is called, it does nothing. Oh, the vector is empty. Return. That's it. It's beautiful. It's a beautiful bit of code. Because, again, you don't see it. You don't see it. You're a first semester computer science student. You do not need to know any of this stuff. You just make a vector and it works. And so for your homework assignment, you can do it in 2 different ways. You can do it using int pointers and call by a pointer. If you want to learn the 80s and 90s style, go for it. Or you can refactor your code. Refactoring means you rewrite it. So you can rewrite your code to use vectors of integers instead. Either way will work. Okay. The destructor isn't triggered. The destructor is always triggered. But the destructor, because when you steal the guts of it, there's something called a move. I don't want to get too detailed, but basically the operation that steals the guts, it's going to set vec into a state where the ending and the starting point are the same, which means it's empty. And then when the destructor is called, it's like, are you empty? Yep. Okay. Peace. We're done. So the destructor still gets called, but that's a trivial, it's a trivial call. Call if, okay, fault, okay, no, done, easy. It's a little bit of overhead, a couple cycles. A few billionths of a second, it's not a big deal. The niceness of this whole thing is well worth it. And in fact, the optimizer could probably optimize that away, because it would probably be able to tell that the destructor would never do anything if the move constructor is called. I would have to check though. I'd have to actually verify that, but I'm pretty sure there wouldn't actually be any overhead to this at all. Okay. And in fact, it might actually implement this by having vec here. Watch this. This might blow your mind. The optimizer could be like, well, I'm just going to make Stover this guy. And so when it's working on vec, it's actually working on Stover out here in main. That's actually an optimization it could do. So there's no return at all. All these pushbacks and things like that would actually just be operating on this variable here. Optimizers are cool. Really neat stuff. So, how would you write it without using a read? Yeah, good question. Let's see here. We got a intent equals 0 ends return. This is the classic, the standard C++. That's it. So, yeah. For this part here, it'd be like string s, cout, please enter a file name. Three lines of code, one line of code. I think you can see why I like my read library better, but if you're going to use standard C++, that's the equivalent of that. Okay. Like silly putty transferring pencil marks. Yeah, exactly. Yeah. Or it's kind of like if you have a sheet of paper, you can either just hand the sheet of paper to somebody, or you can have them copy the whole sheet of paper down. You know what I mean? So you could have them copy the whole sheet of paper and then burn the original, or you could just be like, yo, here's the piece of paper, and just hand it to them. So that's kind of what's going on here. It just moves the piece of paper to the other person rather than copying it and deleting the original, which is wasteful. Okay, so that's it for today, guys. No lab time today. Just work on the Zybooks. Again, there's going to be some things you're not going to know until Monday. Don't worry too much about those. Work on the homework, the bridges assignment. I'm not going to be available. I'm going to be camping. So if you need help, post on the Help Center. Ask the TAs, that kind of stuff, because I am going to be GONE gone. And there's not even cell phone reception, so every once in a while I get like one bar there. But, you know, it's very spotty, because I'm going to be in the middle of the wilderness. So don't ask me for help. I mean, you can. I mean, you know, I'll get to it when I come back. You know, don't get mad if it takes until Sunday night or something. Okay, sounds good. All right, have a great weekend, and I will see you guys on Monday.